some discussions. Today, my aim is to go through all of Notebook 3, and then maybe if people have questions about Notebook 2, we can go back to it. Basically, Notebook 2 was meant to demonstrate that you have to have, your initialization has to be correct in order that if you want to be able to do deep networks, deep neural nets. And he simulated that by making a small fully connected network and a fully connected layer, and then he set up a simulation where he could run that repeatedly and iteratively. So you run the model, you get the output, and then you take that output as the input to your next layer, and then you run it again, and you just sort of recursively run for, I don't know, tens or hundreds of times, and then you see what happens at the end. You see if your weight, what the distribution of your weights is at the end, what's the mean and what's the variance. And what he showed was that if the mean, well, ideally you want to get the mean, you want to be able to initialize the weights in such a way that the mean and the variance will always stay close to 0 and 1 respectively. That is, the mean, you want the mean to stay close to 0 and you want the variance to stay close to 1. And he showed, in that interactive notebook, he showed that if you don't have that, if the initialization is too small, then what happens is the weights tend to go to 0 after a few dozen or maybe less layers. On the other hand, if your weights are too large, then they basically go to infinity or nan, and then you lose the ability to work with the weights. In order to get the weights to stay in this regime that we want, there's a special magic number that you use, and that is there's a multiplier. You initialize the weights with a Gaussian, a zero mean unit variance Gaussian, but multiplied by a multiplier of square root of 2 over n, where n is the number of examples. And if you do that, then he showed that you can repeatedly apply the transformation, and at the end of that, the weights and the mean and standard deviation of the weights will still be reasonably close to 0 and 1 respectively. That's what Notebook 2B was all about. But if you had questions, we could go over that at the end of the meeting. Okay, so I'm going to get started with Notebook 3. And in this notebook, let me just run through it. Let me just sort of scroll through briefly to see what we're doing. First, we're going to get this MNIST data. Remember, it's the digits data set. And then we're going to talk about the softmax, which is what you need in order to make a prediction for a multi-class problem. We'll get into that a little bit later. Then we talk about the loss function that we use for these problems, for classification problems. A bit of that. And then we build a basic training loop. And what he does is he builds this basic training loop, which is, you get the data, you build a model, you run the model, and you look at the answers, and then he starts. So that, and we're about like 1/3 of the way through the notebook now. Then the rest of the notebook, he basically refactors it and makes things better and better and better, so that if you see, this is the training loop here at the beginning, and then through a series of refactorings, he makes it better and better and better. And this is basically software engineering. The results aren't getting any better. The model isn't getting any better. It's just the software engineering part, that is the code part, is getting much better. So at the end, so he built one of the steps through this is, let me just back up a little bit. So I'm going to go back to the original training loop. I'm just trying to draw your attention to how large, to how long it is. It's basically a screen full of code. And I threw in comments there too. So, but it's basically a screen full of code. Then through a series of refactorings, he makes this thing sharper and sharper and sharper. And on the way, we're basically reconstructing functions that PyTorch already has internally. And according to the rules of the game, once we reconstruct it ourselves, then we're allowed to use it from PyTorch. And so that's what he's doing. And he builds this data loader, which is a really convenient thing to be able to get your data in and sample batches and that first you're just sampling the batches from the data, and then he builds in the capability of doing sampling random batches. That's here, and then he said, since we built our own data loader and it does the same thing, we are now allowed to use the PyTorch data loader. And then finally, we're running the model on the validation set and exporting it. But I wanted to draw your attention to the last bit here. Remember that screen full of code that we saw where we're running a basic training loop. Now it's all done in this cell here. It's done in 3 lines of code. And that's what the software engineering and refactoring has gotten us. And this is one of the things that Jeremy's just really all into, is this refactoring and building code that makes things really easy and compact to run, and even straightforward to read the code. You can see what you're doing here. This is so you have the training data set, the validation data set, the batch size, and then you're running this function called get data loaders, get DLs, and then output of that function is the data loader for the training set, the data loader for the validation set. Then you build the model, which is you can just basically read this code and see what it's doing, and then you run the model by means of this fit function. Fit takes as its input the number of epochs, which in this case is 5, the model itself, the loss function that you're using, the optimizer that you're using, and the data loaders that you built that it uses to sample the batches from. And then the output of this function is the loss function and the accuracy. And so here you see what happened. Here's the 5 epochs, and the loss function is after the first epoch is roughly 0.24, and the accuracy is 0.92. Then the loss goes down to 0.15, and the accuracy goes up to 0.95, and so on. We are, let's see, I believe we're running this on the training set right now, I think. But anyway, we'll get into this as we're going to come back and go through the whole thing in detail. 2 people waiting. I don't understand what's going on. The meeting, the Zoom meeting, is different than it's been before. Now, when people join, they get put on a waiting list, and the moderator, that's me, has to notice that they're waiting and let them in. And I just did that. So now we have 9 people in, but I have to keep monitoring I don't know if anybody else can see that. Can any of the existing participants see that list of people who are waiting? Because if you can, I'd like to offload that job of admitting them to somebody else so that, because when I'm talking, I might not notice that they're waiting.
I don't think we can tell. I'm looking to see if it shows up anywhere.
Yeah, I see something that says participants, and it gives me the number of participants, and then it says, then it tells me how many people are waiting, and then it gives me a little button where it says I can admit them. And I wish that would just happen automatically. The interface didn't used to be this way. It only started seeing this last week. See, now I see 1 person waiting. Can you see that when you look at the participants list?
No, it just shows the folks who are already in.
Oh, okay. Now I'm going to admit the person who's waiting. All right, well, I guess that's my job then. All right, and then, okay, so then we got, this is the last cell of notebook, and the very last thing is he does this export thing where, this is where he uses that fire thing that we had to, remember that was part of the installation. He basically turns this notebook into a script and then stuffs it in this directory exp. And the notebook that we're running now is going to be called nb_03.py, and it just gets stuffed into the folder called exp, which I guess means export. So that's what he does at the end of every one of these notebooks. And that makes it available for the next notebook. If you want, you could actually then load that before you run the next notebook. And that's how these notebooks are supposed to work. They're kind of sequential. Each one depends on the previous one. All right, are there any questions up till this point? So feel free to speak up if you have something you want to say. All right, well, let's dive into this notebook. I'm just going to, this is the notebook 3, mini batch. I'll find, if people aren't able to, I shared this, I tried to share it on Slack and on the forum, and if people aren't able to get it, I'll share it in another way. I'll figure out how to share it after this meeting so that you'll make sure to have this copy. Because what I've done here is I've tried to fill in a lot of the blanks, a lot of the gaps. Like these notebooks tend to be kind of cryptic. You don't know what's going on. So I spent a lot of time going through the notebook, and I think I figured out everything that's going on. And I got to admit somebody. I figured out everything that's going on, I think, to my satisfaction, and I've put comments in there to explain it to other people. So hopefully, as you go through this notebook, or as we go through it today, you'll see the comments help us to understand what's going on. All right, so let's start. So first thing he does, he gets does the initial setup. I'm going to run those cells. Then he gets the MNIST data. We've seen this before. Splits it into training and validation sets. And then he takes from their shapes, he takes these N and M. This is the number of rows, and N is the number of rows, M is the number of columns. Then C is ytrain.max. Remember what ytrain is. It's the training labels, and the training labels go from 0 to 9. So ytrain.max, the maximum training label you can have is 9, and then you add 1 to it. Why do you add 1? Because that's the number of labels. So there are 10 different labels. That's C. C is the number of possible output labels. Okay, somebody's waiting. I'm going to admit them. Another person is waiting. Okay. All right. Okay, and then NH is 50. NH is the number of is the size of the hidden layer. I should put that in there. 50. That's what he chose to be the size of the hidden layer. All right. Okay. Did I execute that? Okay. All right. Now he has this a class. He builds a class for a simple, fully connected network. I'm going to run that. We didn't. And this is just building the class. It's not. You haven't instantiated the model yet. This is just a blueprint for how you want to build the model. So you can see what it has, and it has the inputs are the number of input layers. I've relabeled these so that they're more understandable. N in is a number of input. N hidden is the number of hidden, is the size of the hidden layer, and N out is the number of output, the size of the output layer. Jeremy used to have it called NH, and I thought that was a cryptic name, so I renamed it. All right, then this super thing tells you that you get to inherit all of the everything, all of the methods and attributes of the class, of the module class, of the parent class, which is nn.module. You can look up this thing in PyTorch. It's interesting. It tells you what this class is. It's really the basic unit that PyTorch works with is this module. It's a blueprint for a neural net, really. It's how you build a neural net. So this thing initializes this particular class, and then you can see you're building layers into it. The nn.linear is a linear layer. nn.relu is a relu, and nn.linear is another linear layer. So the first linear layer is the input. You know, it's it's input data to the hidden layer. It has n in inputs and n hidden outputs. Then you run the relu on that, and then the last step is to run a linear layer on top of that, which is It takes n. It takes the outputs from the last layer, which is n hidden outputs. That's the number of inputs that this layer has, and then it produces n out outputs. N out is 10 for the digits, possible digits. So ideally, the output would be, it would allow you to take those 10 from those 10 outputs to determine what digit you have. Okay, so when you call this this thing, it sequentially applies the layers. So you're looping through the layers, and you're taking the first layer, applying it to the input x, and then x becomes the output. And then the next step is to take the second layer and apply that to the output of the first layer. And the final step is to take the output of the second layer and apply the last layer to it, which is another linear transform. And then you get the output, and it returns the output. So does everybody see how that works? It's basically, it's building step by step a simple, fully connected network. That's what's going on. Sorry, there's somebody waiting. I'll let them in. All right. Okay, so now we actually instantiate the model. That means actually implement this model into a real object. And this is, so it basically, we give it the inputs, we give it the hidden layers, we give it the outputs, and we actually build this model. And there it is. Now we have a model built according to this blueprint. The next thing we can do is we can predict the training labels, use this model to predict the training labels. So xtrain is the input, and the predictions come out. Here's somebody else wanting to get in. All right, so we run this, the predictions, and then we can look at the output activations for the first training example. So to do this, I cheated. I had to import NumPy. You're not supposed to do that, but what it's doing for me is it's allowing me to convert the tensors into NumPy arrays so that I can actually look at them. So here's the predictions, and then I have to do this thing called detach. I forget why I have to do this. And then I convert it to a NumPy array, and then I look at the first row. And what you can see, the output of our predictions, it's an array that has 10 elements, and each element is some kind of gibberish. It's a small number that can be either positive or negative. And we'll find out why. We'll find out why these outputs look like they do right now a little bit later. All right, so the next thing we have to do is learn about this softmax function. We need to be able to convert our outputs let's see. We need to be able to convert our outputs into probabilities, because ideally what we want in these 10 outputs, we want them to be probabilities for each of the digits, right? So that we can then look at those probabilities and choose the one. Sorry, there's another participant waiting. So that we can look at these probabilities and figure out which digit is most likely to be, which digit our image is most likely to represent. So the output isn't just going to tell us. It's not just going to be a one-hot encoded. It's not just going to say, oh, the digit is a 5. No, you're going to get 10 outputs, and each output is going to give you the probability corresponding to that digit. So you're going to get a probability that the digit is 0, another probability that it's 2, another probability that it's 7, and so on. And then you choose then the highest, the digit that corresponds to the highest probability, and you say, that's my output. Okay, that's how this thing's going to work. Okay, in order to do that, we need to convert these. So by the way, these 10 numbers here are not probabilities yet. They're just activations. They're basically what happens after you apply these 3 layers, the first linear layer, the ReLU, and the second linear layer. These are the numbers that come out. And you can see that they don't look like probabilities because they're negative. Some of them can be negative. So we've got this bunch of activations, and we'd like to convert them to probabilities. And that's where the softmax comes in. The softmax can convert a bunch of numbers into corresponding probabilities. And the way it does it is it exponentiates each number and then divides by the sum of the exponentials of all the numbers. So the softmax for I, let's say I is 5. Okay, so you look at the fifth one, the fifth one, is 0, 1, 2, 3, 4, 5. So here's the fifth one. So softmax of 5 here is going to be e to the this activation divided by the sum of e to the this activation plus e to the this activation plus e to the, and so on, the sum of the 10 exponentials, you see. And this is the way it looks in mathematically. In mathematical notation, it's the exponential of the ith activation divided by the sum of the exponentials of all the activations. And you can see that it's normalized to 1 like a probability should be, because if you sum all of the if you sum all of these softmaxes, that puts a summation on top, and then you can see that it becomes 1. If you sum up all of these things after they've been processed by the softmax, it has that probability that they sum to 1, which is what you want for probabilities. The other thing is they're all positive because the exponential of a number is always going to be positive. So it has those properties that you expect of a probability. They have to be positive, they have to sum to 1, and they have to be between 0 and 1. And again, you can see that the activations have to be between 0 and 1 from this representation. So the softmax is what converts the activations into probabilities. And in practice, what we do, we use the log of the softmax. And that's just because it makes things easier to compute. You don't have, when you work with logs, you're working with much smaller numbers. So he defines this log softmax, which all it does is it implements this formula, return x dot x, that means e to the x, and then x dot x dot sum. The -1 tells you to sum it along the direction, along the horizontal direction. -1 this is a little confusing because it's really hard to find documentation for, if you ever try to look up indexing with a -1 in Python, it's really hard to find a good explanation. So I just kind of absorbed it from what I've seen, and I think that what it means is it means to sum over the last dimension. So if you have an n by m array, and if you have sum along -1, that means sum along the last dimension. Since if it's n by m, that means you want to sum along the m dimension. And remember, m is the columns, n is the rows. So if you have an n by m matrix, n indexes the rows, and m indexes the columns. So summing along the dimension of -1 means sum along the last dimension, which means along the columns. That's what this is doing. So, and then keep dim equals true. I think that means after you finish making the sum, you can actually collapse that dimension and get rid of it, but it says don't do that, just keep it there. And then, so this is chaining, and it's a little confusing when you first see it, this series of operations connected by dots, right? It's basically a very compact way to do a lot of work. So this is collecting the terms, and then this is the denominator has to be summed. So that's what this thing is doing. X dot sum -1 keep dim equals true, and then remember that's this, and then at the very end it says dot log. So that means after you're finished doing this, after you're finished computing the softmax, then it says dot log. Take the log of the whole thing. So that's how you implement the log softmax. All right. Any questions so far? Speak up if you have. Okay, no question. Okay, great. Okay, so next we're going to use the softmax. We're going to apply, as I said, applying the softmax to the output activations converts them to log probabilities. So let's do that. First I'm going to my function, then I'm going to run this. And what I've done is I've just applied the softmax, and it produces something called sm_pred. That's Jeremy's shorthand for, or Jeremy or Sylvain's shorthand for softmax predictions. we run the log softmax on the predictions, and then we look at the shape, and we see that the shape is the same as the input shape, 50,000 examples, and there's 10 numbers in each example. And in this case, those numbers are the log softmaxes. So now we look at the first example in the training set. We look at the softmax prediction. We convert it to an array, and then we look at the first. Actually, this is not the first example because it's index 1, so it's actually the second example. And then, so we're just looking at the second row in SM prediction, softmax predictions, and we see what it looks like. We remember that the output is log probabilities. So you can see these numbers they're negative because they're less. Each probability is less than 1, so the log has to be negative. That's why these numbers are negative. But we're not. I mean, while the output log probabilities are the easiest thing to work with mathematically, the easiest thing to understand is the actual probabilities themselves. So then I said, okay, let's look at the exponential of all these things and see what the log probabilities see what the actual probabilities look like, and that's what we have here. We have this row of 10 probabilities. And you can see that they're all not that much different. But it just turns out that 0, 1, 2, 3, 4, the probability corresponding to 4 is the largest one, right? 0.125 is larger than all the other ones, but not tremendously larger. Look, there's one here that's 0.116, and there's another one here that's 0.109. So 4 wins, but only by a nose, okay? So the predicted digit is 4, but it's not a hands-down no-brainer thing. It's like each digit has some, your model says that each digit has some probability, and 4 just happens to have the highest probability. But that's how we do it. We choose the one with the highest probability.
Joseph, just a quick question.
Yes.
So this might be totally irrelevant. When you've done the softmax stuff, right? Is it the case that you've taken? Is it a numeric probability? Is it a numeric property of this such that when you have these 10 numbers, when you do e to the x of those numbers, of those 10 numbers, and you sum them, that it's equal to 1? Is that just a general property? Because it just seems really...
Yeah, the numbers are positive and they sum to 1, and therefore they have the properties of a probability. I understand what you're saying. There's probably some more rigorous argument that needs to be applied to prove that it's a probability, But
no. My question more is, I've got 10 random numbers there, right?
Yeah. Yes.
Is it the case that I find it odd that if I e to a number and I sum 10 of them like that, that it's always equal to 1? Am I missing something, or is this just a really nice property?
Yes, you're missing something. So let's go back. Let's go back here. Look at this here. Are you seeing where I'm pointing my cursor to?
Yep.
Okay.
Yes.
Now, if you sum all these, okay, so this is the ith one, and it's basically the denominator is always the same. It's the sum of all of them, right?
Yeah.
And the ith one is just e to the xi. Now, if I sum over all of these, what do I get? The 0th one is e to the x0 over all this stuff. The first one is e to the x1 over all this stuff.
Right.
And if I sum them all, I'm going to end up with a numerator that is the same as the denominator. Does that make sense to you?
It does. Thank you. Yeah.
Yes, and then of course, so you get 1. So that's why it's 1.
Great. Okay. Yeah. Thank you.
Okay. Great. All right. So we just got done looking at these output probabilities, seeing what the model is doing. It's going to pick the one. I mean, what we're going to actually do after we run the model is we're going to look to see which digit got the highest probability, and then we're going to say that's my answer. That's my prediction. All right. So that's what we do.
Joseph, just a quick pointer there that you're finding that value which is not that high compared to the others because you really haven't trained yet.
That's correct. That's correct. Yeah, you're right. We haven't trained yet. We're just running the predictions on a randomly on a random initialization. Right. So that's correct. That's a good point. Okay. So next we're going to consider the loss function that we use. We always use. There's a lot of different loss functions that you can do, but the one that you can use for classification problems, but the one that makes the most sense is cross-entropy loss, which is ideal for when your outputs can be expressed as probabilities, because then it makes sense to use cross-entropy. It's one of the optimal ways to, it's an optimal way to find, it's an optimal loss function for a classification problem. There are other loss functions, but the cross-entropy is sort of the one that you always go to when you have classification problems. And what is it? It's, if you have a prediction P, we have to be careful here because a lot of times we think of P as probabilities, but actually our predictions are probabilities. So you calculate the loss for that particular target as minus the sum of the x times the log probability of x. So this would be going across the row. It would be x. X is the real classification. So x in this case is going to be either 0 or 1, and that's the true class. And then log p is the log of the predicted probability. So what you see is going to happen is since x is basically one-hot encoded, it's only going to be either 0 or 1. For the whole row, there's only going to be one value that's 1. All the rest of them are going to be zeros. Does that make sense? In other words, if the true digit is 9, that means that of that vector of 10 values, all of them are going to be 0 except the last one, which is going to be 1. All right. So what that x does is one-hot encoded. It picks out the probability for the true class, and that's what this. And the loss function is then the log of the probability for the true class. And the loss function for the whole data set is basically the average loss function over all the entries, all of the examples. And so that's why I've written this formula here. Capital L is the sum of all the losses for each, data entry, each example, divided by the number of examples. It's just the average over the whole training data set. Okay, so that's the cross-entropy loss. Then he goes through this way of constructing the loss function. He goes through some examples to get you used to indexing, the way indexing works, and he basically says, oh, sorry, there's somebody waiting. Okay, if I don't know how to, I can't talk to the people who are waiting, but if they would send a message on chat and then they could notify me, but they're not in, so they can't send a message on chat. So it's just on me to keep noticing when there's people waiting.
I'll send a message on Slack probably.
Yeah, that would be good, but they don't know that yet. So anyway, I'm just going to keep watching, and hopefully I won't leave people hanging out there. We have 17 people in here so far. All right, so the next section, he goes through a lot of explaining the indexing, the way indexing works. And it works very similar to the way it works in NumPy. I don't want to get hung up in this because there are a lot of examples. But for example, you want to see the training. You want to see our training set. Let's see. Y train. I forgot what the dimension of Y train is. Let me see something. I'll just do it right here. See what Y train looks like. It's got 50,000.
No, I think you want ytrain.size, right? Because that'll give you the dimension.
Oh yeah, that's good point. Good point.
Size bracket. Yeah.
That. Yeah. Okay. So it's basically a vector of length 50,000. So and it's basically it's got these it's got the values of the integers in it. So if you say y train :3, you're basically cutting a slice out of the first 3 values, right? 0, 1, and 2. And these are the digits 5, 0, and 4. Another example, we want to take certain elements out of out of the predictions, and we can do the same thing by looking at size of predictions. See. S_pred size, and we see what we expect. There's 50,000 entries, but each entry has 10. Each entry has 10 values, and remember those values are the probabilities of each of the digits. So what if we want to pick out certain elements, like the 0,5 element? That is the first entry. The fifth, what is the probability for the digit to be 5? The second entry, what is the probability for the digit to be 0? The third entry, what is the probability for the digit to be 4? Well, there's this clever way of indexing that pulls out those values. And so I'm just demonstrating this, and you can see that, yes, that's what you get. Here's the one, the first one that you wanted is this one, minus 2.2. The second one that you wanted is this one, it's minus 2.3. And the third one you wanted is the third row, the probability. It's actually not the probability, it's the log probability that we're getting here. Okay, and so this clever way of indexing, this is implemented in PyTorch just as it is in NumPy. Okay, so that's one example of how you use indexing. Here's another example. We want to pick out the first, second, and third rows, and we want to look at all the log probabilities up to 5, just the first 5 log probabilities. You see, that's what we want. And so I'm just showing you that this indexing, this way of indexing, gets you what you want, and you can compare these rows to what you get. In other words, the first entry here is basically the first row, the first 5 log probabilities, and that's what this is. You know, the second row, the first 5 log probabilities, and third row. I'm just showing you that this way of indexing is doing what you expect it to do. Okay. Next, we look at we already did this, the shapes. And in fact, let me just, since I don't need this, well, it's okay, I'll leave it. All right, so we look at the shapes, we already did that. And now we're going to define this, the likelihood function. Oh, somebody are waiting, admit them. Okay, and this is kind of, I don't know, he defines this in a really round, I don't know, it's kind of hard to penetrate through and figure out what he's doing, but you can figure out what he's doing. Just not, I wish sometimes that when Jeremy codes, he would not write it in the most clever way possible, but in the most understandable way possible. He doesn't always want to do that. Anyway, so he's defining the loss function, and he calls it NLL. The reason is that it's the negative log likelihood loss function. All right, so the input is basically the predictions, and this input thing is the predicted log probabilities, and the target is the true labels. Okay, and so it's going to return the loss function, which, remember, it was this thing. I'm going to go back up here. It's the sum of all of these terms, and each term is minus log p, and then it's the average of. So it's the mean of all of these terms, basically, right? So we want to compute these minus log p terms, and then we want to take the mean, and that's what this function is doing. See, there's the mean at the end. But so you take so there's the negative, and then range of target shape 0 is basically 50,000 because it's got 50,000 entries. And for each entry, we're going to, we want the input, that is the predicted log probability, that corresponds to the actual target value. Okay, so that's what that's doing. So, for example, the very first entry is going to be the predicted probability, that is the input. Okay, remember, input is the SM preds, is the input probabilities. Range of, the first row is going to be the first entry, and it's going to be SM pred of the target, the true value. So if the first digit is 5, I don't know what the first digit is. If the first digit is 5, if its true value is 5, then we're going to want the 6th value of SM_pred, right? That will give us the log probability for 5. In other words, yeah.
Question, Joseph. So negative log likelihood or negative log likelihood loss. Why would we use that? I get the cross entropy. Well, I don't get cross entropy. I just know that for classification we use cross entropy, and then now there's this other negative log likelihood loss. Why would we use this instead? And why is this?
Okay, I get your question, right. The answer is that this is the cross entropy. This is an implementation of the cross entropy loss. I should have made that clear. So what are we doing here? We're actually calculating this guy. We're actually calculating this guy, and this guy. Sorry, we're calculating the this thing, and that is the script L, which is the cross entropy loss. And remember, the script L is a mean of all of the individual loss terms. So it's the mean of these terms. Each one of them is negative, and it's the log of the probability. It's the predicted log probability, right? And that's what we're doing here. There's the negative sign. There's the mean. And what's in here? Input of range target. It's basically taking the SM_preds, the predicted probabilities, and picking out, in other words, the input has 10 columns, right? But what this is doing is picking out the column that corresponds to the actual label, right? So for each entry in this thing that is being returned, it's going to be the log probability that corresponds to the actual digit, the actual value of the label. Does that make sense? So what goes in is 50,000 by 10, but what comes out is going to be 50,000. It's just going to be a vector of length 50,000. I'm sorry, not only that, that's what this would be, a vector of length 50,000, but then it's taking the mean of that vector. So what comes out is a single number, and that is the loss. So let's do that. First, I want to ask, did I satisfy you? Do you understand why this is the implementation of the cross-entropy?
I think I'll just need to take another look at that.
Yeah.
It's not obvious to me right yet.
Okay. I'm going to make myself a note here.
Joseph, just to add to the point, isn't cross entropy the same as taking the negative log likelihood of the softmax function?
Yes, that's exactly right. That's why it's called negative log likelihood. Likelihood is related to probability, and that's what we're doing. We're taking the negative log of the probability for each of the predictions, and then we're taking the average of that, and that number is being spit out as a single number. So let's do that. We spit out the number, and as was pointed out, the loss is high because we haven't really trained yet. We haven't done any adjustments on the parameters. All right, next we do is a refactoring of log softmax. I hope, I know I'm spending too much time. So we refactor the log softmax, and basically this is the same thing. It's just done in a more compact way. If you take the log of a fraction, log A over B is log A minus log B, and we do have a fraction. Remember the thing we're taking the log of is a fraction. We go back to the softmax, So we're taking the log of this fraction, and what we end up with is the log of the numerator minus the log of the denominator. But the log of the numerator is simple. It's just xi, that is. So implement that. That gives us a bit of simplification, and that's done here. And then we check that our loss function that we defined is actually the same as when we refactored it. That's what this test near is. It's looking at it's comparing two numbers or vectors and show, I think it's comparing two numbers and showing that they're the same or within a small tolerance. And that's what we're doing here. Remember the way this function works, this test near works, if it doesn't complain, then it worked. It's basically verifying that they're working. All right, so then there's this there's this trick called the log sum exp trick. And it basically, when you deal with logs of large numbers, you can get into trouble with overflow. And so this is a trick that completely, it's just really ingenious. It basically eliminates the possibility of overflow. Damn it, there's two people waiting. Okay, I just admitted it. All right, so it's just a simple identity. If you take the log of the sum, it's the same thing as multiplying inside the sum by e to the minus a and outside the sum by e to the a. Then you've multiplied by 1, right? So does everybody agree that this first term is equivalent to the second term? Because you can actually take e to the xj minus a as e to the xj times e to the minus a. Then you can pull the e to the minus a outside the sum and multiply it by e to the a, and that gives you 1. So when you take the log of this is a product now. You take the log of a product, it's the log of the first term plus the log of the second term. And so it's the log of the first term is log of e to the a, which is just a. So the log of this thing is this, and a can be whatever you want, but in our case, we're going to define a to be the maximum of all the xj's. And that way, we're never going to get e to the x bigger than 1 in here. That's what the problem is when e to the xj becomes a large number. But by subtracting the maximum off of each exponent, you guarantee that the exponent never becomes a large number. Okay? It's either going to be 0 or some negative number, and that controls the overflow, right? E to the negative number, you don't have a problem with that, because e to the negative number is always going to be smaller than 1. So this is the trick. And here's the implementation of it. First, you find the maximum of all of the x's, and that's what this thing is, x.max of -1. Remember, -1 is the trailing dimension, so it means take the maximum across the columns, and then the 0th element of that. I'm not sure why you need the 0. I'll think about that a little bit later. Anyway, so this is just implementation of that log sum x trick. Run that. And then it verifies that our new log sum x, it still works. It's still equivalent to our old one, and there it is. So now we refactor the log softmax function using our new log sum x function. Let's see. And let's see. I think this dot log sum x is now we're now using the internal Python implementation, the internal PyTorch implementation. And remember, Jeremy's rule says that when we've implemented it ourselves, then we're allowed to use it from PyTorch. So that's what we're doing here. We're using PyTorch's log sum x implementation. So there's our new log softmax function refactored. And then we verify that indeed it does work. We're going to compare the loss as computed before with our new loss function computed using the log softmax function that we just built. Okay, so now that we've built this ourselves, we're allowed to use Python's implementation, and it has an implementation in this functional module, that it has called f. Remember, we imported that at the very top of this thing. And then finally, it combines these two into an internal function called cross-entropy. So now we're allowed, we'll test its internal cross-entropy implementation, and we verify that it's the same as ours. So now we've implemented cross-entropy, and we've shown that our implementation is the same as PyTorch's. That means we get to use it. Okay, so from now on, we'll just use PyTorch's cross-entropy. Okay, now we'll build a training loop, the basic training loop. We first construct our loss function. We're allowed to use Python's internal implementation. And then we construct this little accuracy function. All it's doing is it's comparing our prediction to the actual target. And let's go in here and look at it a little bit. Torch.argmax prediction probs. The input is the prediction probs, which is SM_pred, remember from our previous work, and target, which is, so SM_pred is the log probabilities that we compute, and target is the actual digits, okay? So now, how do we get the predicted digit? Well, we get the argmax of the prediction probs. In other words, we have this row of prediction probabilities, and the index of the largest one, that's our prediction. That's our predicted digit, right? So if the largest one is the second one, then we say that the digit is 1. If the largest probability corresponds to the last element, then that means the digit is 9. So this little thing that I've underlined here, that I've outlined here, is somebody's waiting. So this thing that I've underscored here is the actual is the prediction probabilities, and then we convert it to what is our actual digit prediction. That's what we've got here. And then we compare it to the, well, I shouldn't say what is our actual digit prediction. That's confusing. What is our predicted digit? That's what this thing is. And then we compare it to the actual digit, which is what target has in it. And so we got this vector of Booleans. We convert them to floats, and we take the mean, and that gives us our that gives us our accuracy. Basically, the fraction of digits that we got correct, that's what it is. It's the fraction of digit predictions that we got correct. Does that make sense to everybody? This Boolean statement here compares our predicted digit to the actual digit, and it will be 0 if we failed in our prediction, and it will be 1 if we were correct in our prediction. So then we take the mean of all of these, 0s or 1s, and that gives us the fraction of correct predictions. That's what this accuracy function does. Okay. Next, we're going to define a mini batch of length 64. So we're going to be processing the data mini batch at a time. We define our batch size. That's what BS is. XB is going to be the batch of input data, and we're just going to take the first BS of our the first. Say if batch size is 64, we're just going to take the first 64 samples out of our training set, and then the predictions are going to be running the model on those 64 inputs, and then so then we'll do that and look at the first row of predictions. Remember, the model doesn't find the digit for us, doesn't find the predicted digit for us. It just gives us the output probabilities for each digit. So we're always going to get 10 outputs, and each one of them is going to be the log probability for that digit. And I just look at the predictions and the first row of the predictions, that is, and remind ourselves that the shape is what we expect it to be. It's the batch size. That's the number of rows, and each row has 10 columns for the 10 digits. Right. Next, we're going to calculate our loss function. Once we make the predictions, we can calculate the loss function.
I have a quick question for you.
Sure. Yeah, sure.
I'm noticing there, I think it's in what you just talked about with the batch size.
Yes.
And the mini batch. I remember in the beginning, we did a little cheating where we added NumPy, and this is the reason why. And I wanted to see if you could kind of review that again, where
sure.
Jeremy did something here in this section to allow us to view the tensor, and I think it has to do with that x_train. Do you remember that conversation?
Yeah, he did something which was not cheating, I guess. There's another, instead of doing .numpy, you can do .something else. That's what's in the original notebook, and that's for viewing, and that's if you want to view a scalar. If the tensor just has one number in it, you can actually get it out. You can actually pop it out so you can look at it. And that's what Jeremy uses, but I wanted to be able to look at a whole array, and that's why I used .numpy. I forget what the function was that he used. It's one of PyTorch's internal.
Well, if you just want to see one item, I think it's just
yes.
item, isn't it?
That's right. .item. But that only lets you see one thing, and
correct,
that's why I cheated and used .numpy when I wanted to look at a vector. Okay. Anyway, so I'm sorry I didn't answer. I'm not sure I answered your question, Christine.
That's okay.
Okay.
So when I look at the tensor on 136, for example, the output of 136, right? I can't tell anything from that, right? Because normally, if there were probabilities, then I'd know which is the highest and so on. So this can I assume that this is like this output is meaningless until it's e to the x, and then I make some sense out of the probabilities?
That's right. That's right. You can't tell unless you can do these calculations in your head. Unless you can do the log, the softmax in your head, you won't know which one corresponds to the biggest. Maybe you can do log. Maybe you can do it in your head. Maybe the biggest one is also the predicted digit. Anyway, but yeah, these are log probabilities, right? And we want the and we want the actual probabilities. Anyway, so we get the loss function. It's 2. It's big again because we haven't done any training yet. The accuracy is very low because we haven't done any training yet. Here it's 7% or 0.08%. Okay, but now we're going to actually do the training. So we set the learning rate. We do it. These are the hyperparameters that we're needing. Apparently, I don't know how he decided the learning rate is 0.5, but it works just fine, and it saves us a lot of time looking for the right learning rate. So this is somebody figured this out ahead of time that it's a good learning rate. And then we want to train for 1 epoch, so we set epochs equals 1. Now here's the training loop, and it might be worthwhile. Well, we're almost at the end of our time. Gosh, and I haven't gotten through only a third of it. Anyway, this is the training loop, and what it does is it loops over epochs. So in this case, epoch is just going to be the first epoch. It's just going to be 1. And then for each epoch, it's going to loop over the batches. It's going to construct the batches. So it's going to take the first 64 and then the second set of 64 and so on until it gets to the end. And if the number of examples isn't evenly divisible by the batch size, then you're going to have the last batch, which is going to be, it's not going to be 64. It's going to be whatever's left, okay? And that's what this is doing. I'm not going to go through all the details. Then once we've computed the batch, we then compute the loss function. We compute the gradient of the loss function. We first compute the loss function by making the predictions. That's what this model of XB is. It's the predictions on that batch. And these are the actual labels for that batch. So the loss function then compares those and computes the loss function, which kind of helps us because we're trying to minimize the loss function in order to get at the in order to adjust the parameters. So next thing it does is it computes the gradients of the loss function, and this little command loss.backward does a lot of stuff. It computes all the gradients with respect to all the parameters that we're going to need. Okay, and then finally we update the weights according to the gradients. And so there's let's see, yeah. So for L in layers, remember the layers, there were 3 layers. It's going to go through each of the layers, and it's going to ask if that layer has weights that need to be updated. Remember, of those 3 layers, 2 of them are linear layers that have weights and biases. They're basically linear matrix multiplications. But the middle layer is the ReLU, and it doesn't have any weights. It doesn't have anything that needs to be updated. So when it loops through here, it's just going to hit on the linear layers, the ones that need to be updated. And then it's going to dutifully update the weights and the biases according to our stochastic gradient descent formula. Remember? It's the gradient times the learning rate. It's going to update that weight this way. It's going to do the same thing for the bias. And then before it exits, it's going to zero out the gradients again, so that because remember we're adding and subtracting from these things. When we start the next batch, we want them to start at 0. So that's what we're doing here. We're setting them back to 0 to get ready for the next batch. So that's what this thing is doing. This loop is okay. I'm just going to show you here this has-atch thing that he uses. You can ask if the linear layer has a weight, if the linear layer has a bias. I'm just asking that question, and it's true. Now I'm asking if the ReLU layer has a weight or a bias. And remember I said the ReLU doesn't have any weights or biases because it's simply applying the ReLU function. And so it has-atch tells us no, you don't have any weights or biases. All right, so now we've built this function called fit. Now we're going to actually apply it. We're going to fit this model. Oops, I didn't. I crashed because I haven't executed all of these things. there. Now I should be able to do it. All right, so I trained for one epoch. I computed the loss function and the accuracy at the end of my training. And notice now that the loss function is smaller, way smaller than it was before. Remember, the loss function, when I ran it the first time without any training, was 2 point something, right? Now, the loss function at the end of the training is 0.17, and my accuracy is now 95% after just one epoch, okay? Okay, so now all we're doing for the rest of this whole notebook is we're refining and refactoring, making, oh, I got somebody waiting, okay. Yeah, so all we're doing for the rest of this notebook is refining and refactoring, making things ever more compact and easy and clear, and so on. We're fixing things so that they're easier and easier to use. I won't have time to go through all of that. Hopefully that you will, and bring questions or actually ask your questions on Slack in the middle, in between now and next time. And I think what I'd like to do next time is I'll go through the next notebook 4, but at the beginning of next lesson, we can have questions, whatever questions you have after you've run through this notebook and seen what it does. But again, what we're doing is for the rest of this notebook, all we're doing is we're improving and improving this function fit. We're fixing it and fixing it and fixing it until at the end it consists of just a few lines. So I'm sorry that I don't have time to go through the rest of this. It's fairly straightforward. There's nothing more difficult than what we've already been through. In fact, we've probably been through more difficult concepts because we had to get through cross-entropy, log sum x, the log sum x trick and all that stuff. Somebody waiting? Yeah, so are there any questions up to this point? I'm just going to stop here. And next week we'll take up with the next notebook number 4. Any questions?
No, but nice work, Joseph. Appreciate your time. Excellent.
Thanks, John. Good to see you. Okay, well, I'll let you guys get to your next. Some of you are taking the NLP class, so I'll let you go. Anybody that has questions, you can stay and ask. I'll stay around for a few minutes, and see you next week.
Thanks, Joseph.
You're welcome.
Thanks.
Joseph,
Yes.
did they sort the issue out of having 2 meets, or do you have to shut yours for the other one to open?
You know what? I don't know, so I'm going to shut mine down. I will shut it down right now. I don't know if they've resolved that issue. I think they have. Anyway,
Okay.
I'm going to.
Last time, weren't you on the call for a much longer time?
I don't know. I don't remember. Maybe you're right, but I'm going to shut this down just so I don't want to interfere with the other meeting. So.
Right.
How do I do that? Let's see.
Thanks, Joseph.
Yeah, welcome. Let's see what. Oh, there it is.